Bismillahirrahmanirrahim. So we are back with our new topic, that is the Werner theory, and हमें पता है कि this theory is basically deals with the bonding in the coordination compounds. So it deals basically with the bonding in the coordination compounds. तो coordination compounds को understand करने के लिए ये first theory थी which could actually led finally to the Nobel Prize to Alfred Werner. तो इस theory को आज हम पहली बार यहाँ दिखाएंगे. We can actually finish this theory in an easy way in just 10 minutes. So before we will go to the Werner theory, let us go back to the coordination compounds. So now here मैंने ड्रा किया हुआ एक complex which is nickel hexamine chloride complex. So this is a typical coordination compound. So जो bracket में यहाँ दिखा हुआ, this is called as a coordination sphere. It's also called as the complex ion. And then we have one more sphere which is outside this bracket, long bracket. This is called as the ionization sphere. अब ये जो आप देख रहे हो यहाँ पे nickel, so this is your med line. So in the complex sphere or the complex ion, you have a med line, that's a transition metal, 3D series, and then we have these ammonia molecules which are in small brackets. So this is basically called the ligand. So they are directly bonded to nickel. Their number is 6, which is called as a coordination number. So these are the basic things in a coordination compound. Now, as far as Werner theory is concerned, we'll go straight forward to the what actually, after so many experiments with these coordination compounds, while studying the behavior, you could actually arrive at certain points. Point number 1. जो coordination compounds होता है उसके पास there are two types of valencies. One valence is this which is inside the bracket here, which is occupied with the ammonia. And second is outside the bracket, it's occupied with chlorine. So there are two types of valencies. Number 1. So a coordination compound has two types of valencies. So there are two types of valencies. Two types of valencies. So there are two types of valencies. One valence is called a primary valencies, this one which is outside the sphere. So two types of valencies means one is the primary valency. Primary valency, and second we have secondary valency. So primary valency is which is basically outside the coordination sphere. This is called primary valency. And the one which is inside, that's called a secondary valency. So the postulate number 1. So in the coordination complex, there are two types of valencies, a primary valency and secondary valency. Number 1. Now, so मैंने कहा था we have ligands here. These are called ligands which are inside this complex ion. So ligands are attached. They're basically occupying the primary valency. So we have ligands that actually are there satisfying the primary valency. Fine. So the ligands attached to the primary valencies. This postulate number 2. So the primary valency, which is, let me call it PV. And secondary valency, you can call it as secondary valency. So primary valency, it's satisfied by, or it's occupied by the ligands. So we have ligands there. Fine. While as the secondary valency, primary valency is actually, it's occupied by the primary valency is this one which is outside the coordination sphere. Now, अगर इस compound को आप जो है, if we dissolve this compound, you will get two chlorine ions, 2Cl negative, and one complex ion with a 2 positive charge. So now it has got ionizer, so we say primary valency is ionizable. Ionizable. While a secondary valency is SV, which is basically this coordination number. So अगर आप जैसे आपको dissolve इस complex को आपने dissolve किया, so we'll get this complex ion that will have positive charge and two chloride negative ions. अब इसको this complex ion will remain as it, and that means this is not ionizable. So your secondary valencies, they are non-ionizable. Number 2. So we'll go to postulate number 3. So primary valence are ionizable and secondary valence are non-ionizable. Now, as primary valence is ionizable, this represents the oxidation state of your compound. And it's metal ion that represents the oxidation state. So it gives us information about the oxidation state of metal ion, and secondary valence is it gives us information about the coordination number. So मैंने यहाँ दिखाया है. So this gives information about the coordination number. So that was the point number 2. Now we'll go to the postulate number 3. As far as these secondary valencies are concerned, every metal ion has the secondary valence in a metal ion. They are fixed. And unka number that's always fixed. So the secondary valencies, the number of secondary valencies in a coordination complex, that will be fixed. Fine. So we should say the metal ion has a fixed number of secondary valencies. Fine. That's the postulate number 3. The postulate number 4. Now, the postulate number 4 is now now we have to see which ligands which type of molecules or which type of chemical species will sit in this secondary valency and which will sit in the primary valency. As well as the secondary valency is concerned, secondary valencies will be occupied by, or they will be satisfied by, neutral molecules. Neutral molecules. जैसे इस केस में it is ammonia as a neutral molecule, or it can be a negatively charged ions, negative ions, like it can be anything, chloride, hydroxide, and so on. While as ये जो valence है, it's chloride negative here, two chloride molecules, so it's always satisfied by, so we should say primary valency is always satisfied by negative ions, negatively charged chemical species, negative ions. So this is postulate number 4. Now, so this is the postulate number 1, 2, 3, 4. I will again go to the screen. So the postulate number 1 is that in a complex there are two types of valency, a primary and a secondary, PV, SV. Now, second postulate, the primary valency is ionizable. That will ions. If you dissolve the compound, you get the ions from the primary valency, they will get detached. So that represents the oxidation state. And secondary valencies, they will not get ionized once you dissolve the compound. That represents the coordination number. Now, so the secondary valency, which represents the coordination number, their number is fixed for a particular metal in a complex. Then we have fourth one, secondary valencies. They are satisfied by neutral molecules or negative ions, while as primary valencies, they are satisfied by the negative ions only. So this is postulate number 4. Now if you go to the postulate number 5. So postulate number 5 will drop these things. So we'll go to the postulate number 5. So the postulate number 5 is that if we go to this complex, so we have coordination number is 6 here. So this coordination number basically the coordination number which is here 6. So these are basically these ligands, they are fixed in the space. So I should say the secondary valencies, they are fixed in space. Fixed in a complex, they are fixed in space. So secondary valencies in a coordination complex, they are always directed towards the fixed positions in the space. So they are directed towards the fixed position in the space. That means this gives us the concept of the geometry of a particular complex. Since secondary valencies are fixed in a coordination complex, they are directed towards fixed position in the space. That means they will give us the information about the geometry of the complex. Fine. While as primary valencies have nothing to do with the geometry of the complex. Now, if we have a complex, let's say a metal ion, it has 4 ligands, 6 ligands. So then they are arranged in space in this form that you will actually get, this is your 4 corners on the plane, and then one is above the plane and below the plane. So you will basically have the geometry which is called as the octahedral geometry denoted by OH point group. So that's octahedral geometry. If you have ML6 type complex, that's like here. Inside the coordination sphere we have 6 ligands, so it's ML6 complex. Now if we have ML4 type complex, that is metal, and there we have 4 ligands, then the 4 can be arranged in space in 2 ways. One way is it can be tetrahedral. It can be tetrahedral. So this is one way. Your complex is tetrahedral. Or there's one more possibility that your complex can be a square planar. That is the 4 ligands, they're occupying the 4 corners of a square on a plane, so they can be square planar. So we can, because of those secondary values, you can predict the geometry of the complex. Fine. Now as far as the representation is concerned, मैंने यहाँ पे दिखाया by dotted, this is this bold lines. So secondary valencies, I can show one more point here. So I can write the postulate number 6. So your secondary valencies, they can be shown through bold lines. While as if you have to show the primary valencies, they can be shown through dotted lines. So what does that mean? It means that if I have to show this complex nickel hexamine chloride complex, so as there are 6 ligands, so I will show it here. This is 4. That's your this is now ammonia I will show by L here. Things will become easy. यहाँ पे बड़ा आसान हो जाएगा, लेकिन L से दिखाएंगे. So L means ammonia. So these are 4 on this. This is a plane, a square plane here. So one is above, one is below. So this is your. So these are all the 6 through bold lines, and then we can show the chloride molecules by the dotted lines. So we have 2 chlorines here. We can show the chlorines by dotted lines. Attach it to the central metal line. Some we can show from here. So these primary valencies, they can be shown through dotted lines, while the secondary valencies can be shown through the bold lines. So this is in general the basics of the Werner theory. So I have tried to sum up this Werner theory in just 5 to 10 minutes. So I believe it will be easy to understand, and then if you have any questions, you can just get back to me immediately. So the next class will actually go to our topic, the experimental verification. So the next we will be dealing with the experimental verification in a detail. Experimental verification of Werner theory. Werner theory. So till then, stay with us. This is all for the day.